This is Math 30-1, and we are currently in Chapter 5, which is looking at exponential and logarithmic functions. In this section, we will meet logarithms, and we'll come to understand a little bit about what they are, what they do, and how they're related to exponential functions. So we have measures of success given up here, but let's just jump right into the warm-up question. In a moment, I'll have you pause, but first, as you look at question number 1, you're asked to sketch these two graphs. The first one, y equals 2 to the x, easy to do. You could enter it on your calculator, get some points, plot them, and sketch an accurate graph, please. The second one, you can't enter that on your calculator. So what I would encourage you to do is set up a table of values for y equals 2 to the x. And then notice this second equation here, the x and y are just switched. So switch the x and y, interchange them in the table to figure out points on the graph of this second equation. Okay, so you'll notice those two will be inverses because the x's and y's are interchanged. As you get to number 2, you can enter both of these on your calculator. Now 10 to the x, again, straightforward for entering on your calculator. The second one, y equals log x. If you have an Inspire, your calculator may ask you to put a subscript with your logarithm. And the subscript that you would put is a 10. If your calculator doesn't ask, it's because it's already assuming that this little subscript will be a 10. And then once you have a graph, you could use the table as suggested up here to find some points so you can get a sketch on the grid that you have here. So at this point, I'll ask you to pause the video and sketch the graphs for these 4 equations, and then restart the video. So here's what I've got for that first exponential function. And you can see how I've set up this table of ordered pairs to figure out xy coordinates. And then if I switch these, then I can sketch a graph for the second function. So here I'd look at, well, when x is a quarter, y would be -2. So there's 1, there's a half, there's a quarter, -2. So I'll have a point around there. And then if I continue doing that, then I'll get a set of points that looks like this. And you can see I included this diagonal line y equals x because I was expecting these two graphs, the red and the blue, to be reflections in that line y equals x, because that's what happens with inverses. And we get inverses when we interchange x and y in their equations. Now we can connect those dots as well, and the curves that we get will look a little bit like this. So hopefully you have two graphs that look like that, mirror images in y equals x. For number 2, here we have the graph of y equals 10 to the x. Well, that's the blue graph. The red graph is going to be y equals log base 10 of x. And once again, you will notice that the two graphs are reflections in this diagonal line y equals x, because those two functions are inverses of each other. Here we have it written as a function. Here we had an inverse, but we couldn't write it as a function. We didn't know how to isolate that y. Well, that introduces logarithms for us. A logarithmic function is the inverse of an exponential function. So here's some characteristics we could observe. Because they're inverses, the domain of this exponential function would be all real numbers. Inverses, domains and ranges switch, just like the x's and y's switched. So now we have a range that's all real numbers for my logarithmic function. Again, as we look up here, my domain for this blue function, all real numbers, it looks like it's going up sharply, but it does go to the right forever. Here, my y values, even though it goes to the right fairly sharply, it does go up forever. So we do get a range of all real numbers for that red graph, the logarithmic function. The range for the exponential function, y was greater than 0. That's going to be the domain for the logarithmic function. Again, we'll look here. If we look at this first graph, I have a vertical asymptote here, and then my red function curves to the right. This actually, as well, is a logarithmic function, even though we didn't write it in logarithmic form initially in question number 1. Asymptotes. Well, I've already mentioned that the exponential function has a horizontal asymptote at y equals 0, switch the x and the y, and I get a vertical asymptote at x equals 0. So again, there's my horizontal asymptote for the exponential function, vertical asymptote for the logarithmic function. X and y intercepts. Well, let's look up here. Exponential has no x-intercept, but has a y-intercept of 1. Logarithmic, no x-intercept, I should say no y-intercept, but it does have an x-intercept of 1. So again, the x's and y's are interchanged. There was no x-intercept for exponential, no y-intercept for logarithmic. A y-intercept of 0, 1 for the exponential function, and again, that's without any transformations happening, just the very basic parent function. And we have that x-intercept in the logarithmic function. Well, a little bit more information about logarithms. Log base b of x equaling y. This means exactly the same thing as b to the y equals x. So here I'm not saying that these are inverses, I'm saying that these are exactly the same. Let's back up a little bit here. And let's look at question number 2, because there we can see the exponential and the logarithmic equations. As we look at equation 2 here, if I was to interchange my x and my y, I would get x is equal to 10 to the y. So this will be this red graph. But this is also the red graph. In other words, that logarithmic expression and this exponential expression are identical. Y equals the log, and here I have, pardon me, the y in the exponent where I have x equals the power. So let's look back down here. I have y equals the logarithm. Here I have the y in the exponent and the x equals the power. So these two equations are exactly the same. Those are not inverses. We'll talk about the inverses in a moment. So in other words, what we're saying is, we'll fill in the blanks and then I'll talk about it as I point things out. If x were rewritten as a power with b as the base, then the exponent will be y. That's what this logarithmic statement is saying. Saying whatever is inside here, this we would say is the argument in the logarithm. If I was to rewrite this x so that it was a power where b was the base, oh, well, here is the base b. Here I'm rewriting x. X is equal to, what is the exponent? The exponent is y, which tells me that a logarithm is actually an exponent. So here I have y equals the logarithm. Here I can see the y in the exponent, so the logarithm is an exponent. What's the logarithm operating on? Well, here it's operating on the x, but here I can see that the x is equal to a power. So a logarithm operates on a power, and it is an exponent. Or we could think of this in terms of a function machine. Let's try that. So here you can see on the right, I have a function machine, and my function is a logarithm base b. What it takes as input, any element in the domain is going to be a power. What it gives as output is the exponent. And so what it's doing is it's going to take some number and imagine it's a power where b is the base. So this little subscript that we mentioned earlier, that's important because that tells us what base we're assuming that this power has. So if I put something like um, b to the y into my function machine. I will take the log base b of b to the y. And what does it give me as output? It gives me that exponent of y. It tells me what that exponent would be. A little bit more about the graph. Y equals b to the x. Exponential function. We know that it has no x-intercepts, but it does have a y-intercept of 1. Whereas the logarithmic function, as we looked at in the table above, no y-intercept, but has an x-intercept of 1. Let's continue on. Y equals log x equals y. Well, I should say log x equals y. There we go. Notice there's no base written here. This is called a common logarithm, and as we looked at in the warm-up question, that means that we're assuming that the base is 10. So when there's no base written, then the assumption is that we have a logarithm with a base of 10. So we could write it in. If it's not there, we just assume it's a 10. This next one is a little bit weird. We have ln. On your calculator, it might look like in, but it's not. It's actually an ln, and this stands for natural logarithm with the letters kind of reversed. And what that is when I have a logarithm with a base of e of x equals y. So this is the same as ln of x. Again, this notation says it's a log base e. Now, e is a constant, just like pi is a constant. It's called Euler's constant. Euler is spelt like Euler, E-U-L-E-R, but pronounced like Euler. What pi is to circles in geometry, e is to exponential and logarithmic functions. Now in this course, we're not required to understand or know anything really about e, but it does show up in your workbook, so I wanted to introduce it here. It won't show up on a test or a quiz at all unless I tell you what it's representing. Now look at what we have in our next line. Y equals b to the x and y equals log base b of x. These are not the same thing. Notice this y isn't in the exponent. This logarithm is an exponent, so this y is an exponent. These are the inverses of each other. And since they're inverses, they are reflections in the line y equals x. So these two are inverses. These two, log base 10 of x equals y and 10 to the y equals x, not inverses. These are exactly the same. That will take some practice to get used to. And you may want to back up the video to look at what we were saying on the previous page about those identical logarithmic and exponential equations. As we think about the graphs, first of all, let's think about these two exponential functions. So if I have y equals b to the x, and my base is greater than 1, I get exponential growth like this. If my b value is between 0 and 1, I get exponential decay that curves down like this. For the logarithmic functions, it'll look like this, where here, if my b value is greater than 1, my logarithmic function will increase from left to right. There's the mirror reflection, not a perfect reflection, but it gives you the idea. Here, if my b value is between 0 and 1, my graph will decrease and curve in this direction. And again, they intersect on that line y equals x because they would have an invariant point where x equals y. Well, let's look a little bit more about or at switching between exponential and logarithmic form. So here in question number 7, we have an exponential identity, really. 5 squared is equal to 25. Well, not an identity because there are no variables. If we want to rewrite this in logarithmic form, what we would do is we'd look at this power and say, oh, the base is 5. So if I want to write a logarithm, I would write a log with a base of 5. Notice this is a subscript. It should not be on the same level as that logarithm. So I'm just going to add a line across here just to kind of clarify that notation. And maybe I should make that a little bit thinner. All right, there we go. So log base 5. I got the base from that power. Remember, a logarithm is an exponent, so on the other side of our equal sign, we'll have the exponent. What does the logarithm operate on? It operates on the power. This 25 we can think of as a power base 5, so the 25 would go here. So the log, the 25, the 2, kind of all on the same line here. This 5 is a subscript. Now be careful. It's not 5 to the exponent 25. This 25 is not an exponent for this 5. This log with the base of 5 is a little bit more similar to the idea if I was taking a fifth root of something. I need this index of 5 to describe what this function is doing. I need this base of 5 to describe what this logarithm is doing. So there we have it in logarithmic form. Let's do number 8. Here I can see my base is 4. So I will write log base 4. My logarithm is an exponent, so I'll have this equal to -3. And it operates on the power in disguise here, which is the 1 over 64. And there we have it in logarithmic form. Now, each of these are things that we could evaluate on our calculator. Some of your calculators, you can enter different bases here. And so maybe I should pause to talk about that for a moment. If you have a TI Inspire and it's not in test mode, then you should be able to enter different bases. If it is in test mode, it's possible that different bases have been enabled or it may have been disabled. You'll want to get it out of test mode to enable that change of base option. If you have a TI-84 Plus, then depending on your operating system, you may or may not be able to enter different bases. The way you would do it is you would hit the alpha button and then the window key. So that brings up the F2 menu of options. And number 5 there is log base something. I will attach a video in Edsby for my students to kind of see that more visually because I don't have a calculator I can show you right here. But we could plug it into the calculator that way. Let's go on to number 9. Again, I look at my two sides. On the left, I can see the power. So I will write the log with a base of 1/2. Now, when we have fractions in the base, you don't have to, but often we'll put it in brackets just to make it really clear that entire thing is the base. Over here, we put the argument in brackets. Wouldn't have to, but again, for clarity, to separate it from this 4, which is the base, to make it clear that this is the argument, that's what we chose to do. So here I'll use another bracket to say this will be the 1 over 128, and then this logarithm is equal to the exponent of 7. So let's just kind of back up a little bit and think about what the logarithm is saying for a couple of these. As we look at number 7, remember that a logarithm says, if I was to take this 25 and rewrite it as a power base 5. So I have log base 5, and I'm going to take this 25 and rewrite it as a power base 5. Oh, that's 5 squared. What would the exponent be? It would be a 2. So the logarithm takes this power as input, and it says, if I rewrite this 25 with this base, this is the exponent it will give me as output. We'll do more examples like that on the next page, so I think I'll leave that here for now. Now let's go the other direction. We have logarithmic equations, and we want to write it in exponential form. Again, I like to start with a base. That makes it easier for me. So my base is 5. I remember the logarithm is an exponent, so my exponent is 4. And this is equal to the power in disguise, which is 625. And when we write it in this form, it's a little bit easier to say, oh yeah, this is a true statement, because 5 to the 4th is 625. Number 11, my base is a root 2. The logarithm is an exponent, so the exponent is 6. And this will equal 8. And again, I could do some simplifying on this side just to confirm that that's true. Number 12, no base given, which means I have a base of 10. Common logarithm, there's my base of 10. A logarithm is an exponent. There's my exponent. That's equal to the power, what the logarithm is operating on. It's a power in disguise. And so 10 cubed equals 1,000. Well, before we go on to more examples like this, let's think a little bit more about uh, function machines and the relationship between an exponential and logarithmic function. So I'd like you to pause the video in a moment and then write down here what is the composition of functions that this function machine is picturing for us. So again, we've looked at function machines a little bit in the past. What would the expression look like to complete this equation? And then similarly, we're going to do this composition of functions. What would that composition look like? So pause the video at this point and then restart once you've finished these two questions. Well, if you remember the order, my x, whatever it is first going into the exponential function. So this would be my inside function. That's going to do something to the x first, and then the logarithmic function is going to operate on it second. So this is what the equation would look like. Here the x goes into the exponential function first, and then into the logarithmic function second. It's just reversed in the next one. So first, we're in the logarithmic function, and then in the exponential function. And as you'll recall, we said these two are inverses, which means the output that I'm getting should be the same as the input that I initially stuck in. So here I put in an x. It went into this 3 to the x. What I'm getting out here is a 3 to the x. So then this x is replaced with the 3 to the x. And remember what a logarithm is telling us. It says if this power, 3 to the x, were written as a power with a base of 3, oh, it does have a base of 3, the logarithm would tell me the exponent. What's the exponent? The exponent is x. So this is equal to x. This composition is often a little bit easier than the next composition, but these two are still inverses. So now when my x goes into the logarithm and then it gets put in the exponent of the 3, if the base of the power and the base in the logarithm that's in the exponent, if those two are the same base, this is equal to x because they are inverse functions. Now let's look at a couple more examples. Now here I put in some statements that aren't included in your notes, just again to get those words in our head. We want to evaluate each of these logarithms. So here, if something were written as a power, well, as I look at this, what's the something? Well, that's what the logarithm is operating on. So if 3 to the exponent 4 were written as a power with, I'll look at my logarithm and the base is a 3, so with 3 as the base, what would the exponent be? Well, that's pretty straightforward. I can already see my exponent is a 4. So this is equal to 4. This is what the logarithm is telling me. Number 14. If 16 were written as a power with 2 as the base, what would the exponent be? Well, let's just go through some steps. Log base 2, 16 is 2 to the 4th. So what is the exponent? The exponent is 4. That is the value and the meaning of the logarithm. Number 15. If my argument here, the 0.001, were written as a power with 10 as the base, what would the exponent be? Well, let's think here. This is a log base 10. If I think about the place value, this is the tenths, hundredths, thousandths. So that's the same as 1 over 1,000. Then I'm just going to come down here because I have more space. So this is the log base 10 of 1 over 10 cubed, which is the same as the log base 10 of 10 to the negative 3. So if 0.001 were written as a power base 10, which is what we did, what is the exponent? The exponent is a negative 3, and that's what the logarithm tells us. Why don't you pause and try the next ones? They are getting more challenging, so if you get stumped, don't worry, just restart the video and we'll finish it off together. Number 16. If 1 were written with a power where b is the base, what would the exponent be? 1. Hmm. Well, we know anything with an exponent of 0 is equal to 1. So we have the log base b of b to the 0, because b to the 0 equals 1. So what is my exponent? It is a 0, and that's the value of the logarithm. So notice the logarithm can have an output of 0. So sometimes we get confused when we see the 0 because we think, oh, well, it only goes to the right of the y-axis. But that tells us x can't equal 0. But we can get a y value of 0, and that, in fact, that is the x-intercept. So that's what we got in number 16. For number 17 and 18, I didn't write down the question again, but it's in my head, so I'm still going to use it. If this number in the brackets were written as a power base 2, the logarithm will tell me the exponent. So let me work at that. I want to rewrite what I have in the brackets there as a power base 2. Now, in this situation, where this 3 is kind of in between, we're wondering, oh, is that an exponent, is an index? Always assume it's an index if it's immediately in front of a radical like this. If it wasn't there, then there would be more space in between here. So I have 2 to the exponent 1 times 2 to the exponent 1/3. And again, that's because I have a cube root of 2. Multiplying powers with the same base, I can add their exponents. So this one is the same as 3/3, so this is 2 to the exponent 4/3. So I've rewritten this 2 times the cube root of 2 as a power base 2. The logarithm, base 2, tells me the exponent, which is 4/3. Last question. Well, I have a similar situation, but I'm going to start by just rewriting this as 2 to the exponent 4/3 because my argument is the same. The problem is, how do I rewrite this 2 as an 8? Well, we could manipulate our way around this, and let me do that, and then I'll show you another strategy we could use. So I have log base 8. 2 to what exponent equals 8? 2 to the exponent 3. Okay, 2 cubed. How am I going to get this exponent to look like 4/3? Well, it's kind of like here. if I have a power raised to an exponent, I multiply those exponents. So here, if I'm multiplying by 3, over here, I want to divide by 3, right? Because if I was to multiply these out, this 3 would be in the numerator, cancel with that 3 in the denominator, and I'd get a 4/3. Oh, that's a little tricky. Who would think of doing that? Well, I did just at the moment because I knew it was coming. But that gives me 8 to the exponent 4/9. Now I have a base of 8, a base of 8, and this is equal to the exponent of 4/9. Well, that was pretty crazy. So what other options do we have? Well, let's back up and look at some of these other questions. Let's start with number 14. And I'm just going to rewrite that original question. Log base 2 of 16. I want to know what this is equal to. So what I'm going to do this time is I'm going to say, well, let's just pick a variable. Let's suppose it equals x. We learned on the previous page how to rewrite this in exponential form. So let's do that. Here, the base is 2. A logarithm is an exponent, so the exponent is x. This equals this power, the argument that the logarithm is operating on, that's equal to 16. Well, this type of equation we've already solved before. So I have 2 to the x, and I can rewrite 16 as 2 to the 4th, which tells me my x is equal to 4. Now, my original question didn't have an x in it, but what it did have was this log base 2 of 16, and I said it's equal to x, so that means that this 4 is what log base 2 of 16 is equal to. Same answer as we had up there, just a different route to get there. Now you might say, well, why didn't you show me this first? It's so much easier. Well, that's why I didn't show you it first, because then you wouldn't think through what a logarithm is actually doing. And I want you to understand what a logarithm is actually doing. But when we get to a question like number 18, it's a lot easier if we use that strategy. So there are times that we'll just do it. So I'm going to take this and set it equal to x. And then I'm going to rewrite this in exponential form. So let's come down here. My base is an 8. My exponent is an x because the logarithm is an exponent. And this will equal 2 times the cube root of 2. Then it's a little bit more manageable, because on the left side, I can actually change this 8 to a 2 cubed, all to the x. And then on the right side, as we saw before, this will be a 2 to the 4/3. Simplifying a little bit further, 2 to the 3x equals 2 to the 4/3. Power equals power, base equals base, so the exponent of 3x equals the exponent of 4/3. Divide the 3 over, and I get same answer. There we go. So time for some practice. And let's look at these measures of success. Can we explain how logarithms and powers are related? Well, yes, we can. We can rewrite a logarithm as a power, and a power as a logarithm, and logarithms and powers can be inverses of each other, depending on how we format it. I can rewrite a logarithmic equation in exponential form. That's what I did in this question. And an exponential equation in logarithmic form. We did some practice of that on a previous page. I can describe the characteristics of the equation and the graph of a logarithmic function. Well, that feels like a long time ago in the lesson, so you may want to go back and review that before you check this box. That ends this lesson, though.